I think we're finally going to make the last talk on time, and thanks for staying for the very last talk for this morning session. And we're very fortunate to have Chinmay. He's a PhD student, third year PhD student here at UC Berkeley, and he will continue discussing Minmax optimization in the convex-concave settings. Yeah. So without further ado, yeah, please take it away.
Okay. So hello everyone, I'm Chinmay, and I'll be today presenting on our recent work on zeroth-order methods for convex-concave min-max problems. And we present a new application for the min-max domain, which is learning robustly from strategically generated data. This is a joint work with these four wonderful people. So let's get started. So as we all know, machine learning algorithms have occupied our lives a lot in these days. A typical machine learning algorithm pipeline looks something like this. You have some data which is sampled from some static stationary distribution. You do some optimization, you throw away some optimization algorithm on top of it to minimize certain loss function, and out comes a predictor or classifier in most of the settings, which will predict what should be a label or what should be the value of the data point which you are injecting at the test time. So a central dogma in machine learning is, as I said, that observations are independently drawn samples from a static distribution, which is representative of the reality. And this kind of thinking has worked out reasonably well in a lot of settings, which we see today, for example, like object detection, recommender systems, and even in the fields like data-driven material discovery. And there are a lot of examples for this, so I will not bother you guys with this. But there are certain challenges which we must address timely in order to develop next generation machine learning algorithms. So I will present two such challenges and will provide what work we have done in resolving two of those challenges in some way. So the first challenge is that of distribution shift and bias. I guess a lot of speakers have talked about this in this workshop series. The distribution shift problem is essentially that you cannot rely that the data is coming from a fixed stationary distribution. There can be certain adversarial interceptions in your data set, or simply because some of the environment in which you are using your algorithm is non-stationary. So you need to consider that effect while designing these algorithms. So one such very interesting unfortunate incident which happens when we use machine learning algorithms, if we don't take into account such challenge, is that of a predictive policing algorithm. So these days, a lot of cities use these predictive policing algorithms, primarily a machine learning algorithm called predpol, which decides how to allocate the policing resources into some neighborhoods in the city in order to reduce crime or drug users or something like that. So this is a particular study which came out in 2016, which talked about how were the drug arrests being conducted in our neighboring city, Oakland here. It turns out that the data set which that machine learning algorithm was using was slightly biased because of some historical reasons towards some particular neighborhood in that city. And the data set was primarily saying that the drug users were concentrated in primarily two camps here. While the reality is that there were some surveys which showed that, in fact, the drug users were like more or less uniformly prevalent in almost all of the city of Oakland. What this kind of data set has led to is that these predictive policing algorithms will now mostly predicting that police go into these particular areas, which are denoted by red here only, and avoid the other areas, which, by the way, as per the ground truth, has more or less the same crime rate. So this kind of bias which was further propagated by use of this algorithm. In fact, it turns out that this sort of output for this algorithm was kind of unfair to people of color because it led to a higher percentage of arrests for people of color as opposed to people not of color, while in reality the drug uses was more done by the people not of color. So one has to be careful while designing machine learning algorithm which has some such societal implications. And it turns out that this previous article, which came out in 2016, we have not done much better, because there was one recent article which came out in 2021 as well, and which kind of emphasizes again on this issue of these crime detection algorithms. There is this other issue comes out when you use these machine learning algorithms in environments which comprise of some strategic agents. So strategic agents will have certain incentives which they want to maximize, and that incentive might not align with whatever was the main purpose for which that original machine learning algorithm was designed. So there is one more similar example which kind of shows this challenge, which is about Uber search pricing. So recently there have been some incidents where the drivers which use Uber app colluded, and then they turned their availability off, and which led the search pricing algorithms to increase the prices for the customer, and in fact it led to higher prices for the customers. So one has to now think about designing these algorithms in a closed loop fashion. What do I mean by that? So this is one of the typical machine learning problem which all of us are aware of. But based on the challenges which I presented before, one has to also consider this, the effect of adversarial perturbations to the data set, and also how does the outcome of your machine learning algorithm in turn affects the data which is being fed into that algorithm. So one has to thus, what we will be dealing today primarily will be about robust decision dependent machine learning. I'll define these words more precisely in the later slides. There are two primary questions here. So one question is about how to handle the robustness to some adversarial perturbations data, which a lot of people have done, which goes by the name of robust optimization and whatnot. And the other question is how to model. How does the outcome of the machine learning algorithm changes the data? So there are two questions primarily of modeling and robustness. Okay, so today the main focus of this talk will be about how can we design a game theoretic abstraction to the problem which I just presented, and how can we tractably reformulate that problem into a meaningful problem which can be solved easily. And next, taking inspiration from whatever reformulation we get, we also extend the min-max optimization, the designing of min-max optimization algorithms in a particular framework, which I'll present later on. Okay, so let's just think about the problem which I was talking about in a very high level. What does that problem look like? So we all know in typical machine learning optimization problem looks like you have some data Z, which is sampled from a probability distribution P, which is static, stationary, and you minimize certain loss function where the loss function is parameterized by data and the parameter which learner wants to learn and which learner wants to learn by minimizing this objective function. But while taking into account the issues which I presented on the previous slide, there are two concerns here. One concern is about dealing about the uncertainty set which you have, which comes because of an adversarial intersection in your data set. And also there has to be a component which models how the action or the outcome of the machine learning algorithm changes the data set. So it turns out that this problem now becomes in sub problem. If you assume that the parameter theta lies in some finite dimensional land, but whatever you are optimizing over here in the sup variable, in the sup part is kind of an infinite dimensional object. You are dealing with probability distributions here. Okay, so let's just specialize this setting a little bit to consider a particular application, because the previous problem was very general. So here we consider a specific application of generalized linear model where the loss function takes this specific form. One example of this could be a logistic loss, which is used in a lot of label prediction algorithms. And let's consider this task of predicting label y, which is plus or minus 1, given any feature x. A typical risk minimization we know will solve this problem, as I already said. It turns out there has been some work which also takes into account the modeling question which I raised, that how does the outcome of your machine learning model in fact affects the data set, and which was studied in these works of strategic classification or performative prediction, which talked about what happens when your probability distribution from which you sample data set depends on the learner's parameter theta. There has been another domain of machine learning research which talks about robust risk minimization, which typically studies these problems of distributional robustness. When you assume, when you relax the stationarity assumption of your sampling distribution, and you say that the distribution from which you sample data set lies in some uncertainty set, which is denoted by D here. And we now in today's talk will kind of combine these two lines of thinking and present a robust framework to tackle this decision dependent aspect of machine learning. So we'll be primarily focusing on this sort of problem today, where the probability distribution comes from an uncertainty set, which depends on the learning parameter of the learner. Okay, so let's just get because since again we have to put some structure to get some meaningful results out of it, we'll deploy certain structure on how the uncertainty set looks here. So there has been some work in the distribution robust optimization land, where people have kind of considered the reformulating this infinite dimensional optimization problem by suitably placing assumptions of that the uncertainty set be moment bounded based uncertainty set, or it be a ball in a Wasserstein metric, or there are a lot of these reformulations. But in today's talk, we'll mostly focus on the setting where the uncertainty set is a Wasserstein ball of a specific radius. So here to get how does the outcome of your machine learning algorithm affects the strategic behavior which we want to observe. So we assume a particular structure on how does the agents behave in this setting. So let's say we have n agents whose ground truth labels are denoted by x bar, y bar, which are sampled from some distribution d bar, which is their ground truth distribution, which is the distribution prior to when they have responded to the classifier, responded to the learners, responded to the machine learning algorithm. We assume that agents will have certain utility function, and this utility function is heavily studied in this strategic classification setting, where we assume that the utility function which agents have is they want to be positively classified for certain application domain. For example, a bank granting loan, people would want to fund the bank to grant them loan. So that's why this first term, blue term, which denotes they want to go on the positive side of the classifier. And the second term, that this shift in their features will not come for free. They have to pay certain cost in some sense in order to change their features. And that's why this pink term here will denote the cost which agents have. If you impose certain assumptions on like convexity and homogeneity on this cost structure, you can be sure that whatever be the best response of these users will be a convex function in theta, and which has been shown in a paper Dong et al. In 2017. So what our goal here today is, we just want to state that this robust decision-dependent problem can also be recast as a convex-concave min-max optimization problem in a finite dimensional space. And to do this, we just use, as I said, that there has been some work which showed if you assume this sort of utility structure on agents, will guarantee the convexity part of it and the duality part, which ensures that you convert this infinite dimensional problem to a finite dimensional problem, comes from the Wasserstein distributionally robust optimization, which has been independently studied in 2 works. Okay, so having said that, I will not spend too much time on how does the actual optimization looks like, because what I want to emphasize more on this talk is about the algorithm which we have proposed, which is inspired from this kind of thinking of min-max optimization. So what we observe that in these strategic settings, whatever algorithm we use to solve this min-max optimization needs to fundamentally satisfy these 2 requirements. One, we will not have the exact utility function which agents out there are using in wide. We will only get whatever response agents do to the learning algorithm which we are using. So that's why our algorithm should be based on some sort of a zeroth order optimization, because we cannot take gradients and stuff like that. And also, since here we are dealing with agents or human beings at large, we cannot query them a lot of number of times. So we also want to minimize the number of times we query such individuals. So that will be the next focus of this talk, where I will talk about a practical algorithm, which one of the use case of that algorithm is this application, and that can be used in a lot of other applications as well, which is a convex-concave min-max optimization algorithm. Okay, so let's just briefly recap what a min-max optimization, what developments we had in the min-max optimization land. I agree, a lot of speakers before me have already emphasized this point very, very clearly. But just for the heck of it, I'll quickly go over the slide, which talks about the min-max optimization. So min-max optimization looks something like this, and the typical application areas for this kind of optimization algorithm is robust machine learning algorithms, where people want to be robust against data poisoning attacks or data evasion attacks. One of the popular setting which has like popularized min-max optimization or game theory in the community, or the machine learning community, is that by generative adversarial networks, which was proposed in 2014. There are some recent work which have also cast the distributionally robust optimization into a min-max framework, in a finite dimensional min-max framework, which can be computed very quickly using specific algorithms. Also, in any engineering design, if we want to talk about the worst case design, we always use some sort of a min-max optimization, where we maximize over certain actions taken by an adversary. And there are some quite recent applications which talks about the fairness of machine learning algorithm in this, and apply such techniques, such algorithms to solve that. Okay, so I think I cannot do justice by talking about all of the min-max learning algorithms in just one slide. I'll only denote those algorithms which are related to the work which I'll be presenting in next few slides. So as I said, we'll be using mostly a zeroth order algorithm or a gradient free algorithm, because of the applications from which we have inspired this. So there has been a lot of progress in the area of designing gradient based algorithms, and there are a lot of algorithms as shown here which kind of have very quick rates and can get you to the min-max, the saddle point of the min-max solution very, very quickly. The progress in the gradient free setting, I would like to say, is not that much. It's still kind of an evolving field. People are kind of analyzing certain variants like strongly convex, strongly concave setting, or some sort of other curvature requirements in either X variable or Y variable. And there have been some work which talks about the convex-concave optimization, and just use the smoothness of the problem and not just any curvature on the objective function. Okay, so today I'll use these two main algorithmic thinking paradigms of optimistic gradient descent ascent and convex. I'll be working in convex-concave setting and with just a smooth objective function. Okay, so let's just quickly recap optimistic gradient descent ascent algorithm, which was I think initially proposed in 1960s or 70s, and it has recently found out prominence in training of GANs after a paper by Daskalakis in 2018 or 2017. So the problem which we consider here is that of the same problem, min-max of a loss function. Since we will be dealing with certain data which is sampled from a distribution, we will typically have this finite sum structure of the loss function. And this loss function is assumed to be convex-concave, and the sets are the convex and compact sets. We all know what a gradient descent ascent algorithm looks like. This algorithm will take the current iterate and move along the negative of the gradient with respect to X direction in the X variable, and similarly ascent along the gradient of the loss function in the Y direction with particular step size, let's say eta. It has been shown that It has been shown that the gradient descent ascent, if you work with unconstrained setting, I guess a lot of speakers before me have talked about it, the iterates of that algorithm diverges even for a simple loss function like x transpose y, which is linear in x and linear in y. To tackle that, there was an algorithm proposed, which is optimistic gradient descent ascent, which kind of directs the iterates in the right direction by appropriately adding these error terms into the update of your equation. So this kind of figure denotes like how the k minus 1 and k iterate is used to update for the k plus 1 iterate. Okay, so this was a preliminary on optimistic gradient descent ascent. I'll also quickly recap what a gradient free setting looks like. So what in this work we'll do is we'll just replace the gradients, the actual gradients, with an estimator of that gradient. And a typical estimator which people use is this randomized estimator, which I'll present on this slide. So consider a function L which is from a space Rd to R. The estimator of a gradient of this function by just using the function values of this function is typically constructed by by this kind of equation, where what if you want to compute a gradient at a particular point x at a particular direction v, what you will do is just perturb the point x in an epsilon ball around that point, and you will sample a point v from that sphere uniformly randomly from that sphere and construct this estimator, which is computed by just d over epsilon times the loss function times the direction which you are using. I think in this current form, it may not be very intuitive, but if you want to think about this estimator for the case of d equal to 1, this estimator, the expectation of this estimator looks something like this, which is in one dimension, the sphere is nothing but just a uniform distribution half on plus and minus 1. The expected value of this gradient estimator then looks like L of x plus epsilon and minus L of x minus epsilon over 2 epsilon. And this is like typically what we use in a lot of engineering applications when we don't have a gradient. It's a 2-point estimator, as a lot of people call it. It turns out that this gradient estimator may not have the property of unbiasedness, in the sense that the expected value of this gradient may not represent the actual gradient of the loss function, but one can say it's close enough. The expected value of this gradient estimator is in fact the gradient of the original loss function, but this loss function is now smoothed out in an epsilon ball around every point. So it is basically doing this sort of expectation where you sample a direction uniformly from a ball and you just smooth out that function in a ball. It turns out that the bias of this estimator varies directly with the perturbation radius epsilon, which we use in order to construct this estimator, in order to construct the zeroth order estimator. But it turns out that the variance will also grow if you kind of decrease epsilon in order to improve variance. So you have to kind of trade off between and choose one particular specific epsilon in order to get the best possible estimator for your setting. And as it will turn out in the theorems which I present later on, this kind of fact or this kind of thinking will re-emerge again. Okay, so as I said, the main algorithm which we will be talking about today will be a practical algorithm. So in a lot of these finite sum structure kind of loss functions, practitioners typically do not sample data point uniformly randomly from all the data points. What they will do, they will run the algorithm in epochs, and in every epoch they will fix a permutation which is sampled uniformly randomly, and then go over the data set according to that permutation. And that is what is typically referred as random reshuffling. There has been a flurry of research in the area of kind of giving rates for this practical algorithm in the optimization land. And these two are, like, I believe one of the main papers which kind of lead this domain. But what we want to do is we want to use this kind of thinking for the min-max setting as well, and try to see how does these algorithms perform in this setting. So just to give a very high level overview of the algorithm which we are using, it's nothing fancy. We just use the OGDA update with a zeroth order estimator and run a random reshuffled version of this algorithm, which is denoted here, as I said. So you run this algorithm in epochs, which is denoted by little t. In every epoch, you will sample uniformly randomly from a permutation of set of all numbers from 1 to n, and then go over data set one by one as per that permutation. And in the next epoch, you will resample and do this process again and again. And finally, we will output an averaged iterate in this setting. So to the best of our knowledge, the algorithm presented here is the first zeroth order random reshuffling algorithm for a min-max problem. Okay, so let's look at how does the convergence of this algorithm look like. So before talking about convergence, one has to think about what do you actually mean by convergence in a min-max optimization. While we are solving any optimization problem, the convergence simply means you decay your loss function in the subsequent iterates. But in min-max optimization, it's not quite clear because both the operation minimization and min-max maximization are happening simultaneously. So it turns out people use a variety of metrics to show convergence. Some people use stationarity conditions to show stationarity conditions as a metric that how far is your gradient being not zero. But it turns out in the convex-concave setting, you have a very good structural metric which you can use in order to evaluate the performance of any point, or in order to evaluate how that point performs on the min-max operator. So we define this thing called delta, which we'll refer as gap. So given any point x and y, we compare the loss function or the objective function at a point x and y star, and take a difference with point x star and y. So now what are these point x star, y star? So x star, y star are the actual solution of the min-max problem. Okay, and it turns out that this quantity has good property in the sense this is always greater than equal to 0, and it takes 0 value only at the saddle point of the convex-concave min-max problem. Just to see quickly why like this kind of operator is good enough, if I write down this operator again and add and subtract these terms L x star y star and L x star y star, it turns out that the first term, which is shown here, we have fixed y. So, and by the min-max operation for any y, the x star kind of minimizes the objective function if you fix y to y star. So that's why this quantity will always be positive. And similarly, if you fix x star, y star is the point which maximizes the objective function. So this quantity will always be positive. Okay, so after establishing that this delta is kind of a good enough metric for kind of looking at the min-max problem in the convex-concave setting, I'll present the theorem which we have for the optimistic gradient descent ascent algorithm with zeroth order gradient and random reshuffling, quite a mouthful. It turns out that if you run that algorithm for t epochs, and if you choose these step size, which step size here is the step size which you use in the optimistic gradient descent ascent algorithm, and the perturbation radius epsilon, which is the one which you use to compute the zeroth order gradient estimator, in such fashion, then this gap function kind of decays at the rate of t to the -1/4. Right, and the choice of these etas and epsilons are typically governed to kind of balance the bias variance trade-off which we obtain from the zeroth order estimator. Okay. One would say, can we improve? Like this may not look very promising rate to work with. Can we improve this rate? So it turns out in this setting, we were using a very naive zeroth order estimator, which was just 1 point estimator that you compute the estimator by just evaluating the loss function at 1 point. It turns out if you use a 2 point estimator, which kind of instead of doing L of x plus epsilon v, you also subtract L of x minus epsilon v. You can improve this rate to d square over square root t. I think I forgot to put a d here. It's a d square also here. So it depends on the dimension of the variables which you are working with. And you can improve the convergence rate by square root t. It turns out we are primarily working with this kind of rate, or this is the first thing which I'm presenting here, because if you remember the application which we inspired the min-max optimization, where we had one desiderata which talks about that we want to minimize the number of queries. So if you are using multi-point gradient estimator, you are naturally increasing more and more queries for your algorithm. But it turns out that there is much more to this problem than just that. And in fact, no one has ever analyzed this optimistic gradient descent ascent algorithm or a min-max algorithm with a random reshuffling variant with just using a first order information. It turns out you will drop this d square term as well, and you will get a rate of 1 over square root t. If you remember, this d square was primarily coming by the way we were constructing the zeroth order estimator, where you had d over epsilon times the function value. Okay, so I'll quickly go over the proof sketch. To think about the proof, there are primarily 3 main results which we use to get the final rate. I'll present these 3 results one by one. So if you remember, the first sort of bias which comes is introduced is by the random reshuffling. As I presented on the previous slide, the random reshuffling, in every epoch you fix the permutation over which you will go for that particular epoch. And so in every time step when you use the algorithm, the iterates are not uncorrelated, as was the case with the SGD update, because there you sample a new data point independently, uniformly randomly at every time step. So you naturally have you introduce some correlation due to using random reshuffling. So one has to kind of deal with it. So this is the first result, which talks about the bias which is introduced due to random reshuffling. So note that the bias here will affect the gap function. If you recall, the gap function was just the difference operator which I just defined, which was L of x y star minus L of x star y. It turns out that this gap function which we obtained, gap function evaluated at the iterates of this algorithm which you obtained after reshuffling, and the one which you obtain without reshuffling, you can bound it by following the random reshuffling literature in the optimization landscape by just the difference between the iterates which you obtain by 2 specific sequence of permutations which differ by just 1 entry point. In a sense, if you give me two particular permutations of the data points 1 to n, which differ in 1 point in a specific manner, then you can show that this kind of bias which is introduced due to random reshuffling can be bounded by the difference in the iterate values and just summed over all the 1 to n. I think this is not one of the main contributions of this work. This is how typically a random reshuffling algorithm is being analyzed in literature, is that you kind of construct 2 iterates which are coupled with one another, and you kind of bound the Wasserstein distance between the 2 iterates, and you further bound the Wasserstein distance by this 2 norm, which comes out naturally from the definition. I think I will not go too much in detail for this lemma, because I think it will introduce, if I'll need to go into specific, I'll need to introduce a whole lot of notations which are not relevant to the main core of the proof here. The other core, the main thing which we use here is one of the main proof techniques, new proof techniques which we introduced in the min-max literature, is this second lemma, which talks about this particular, how to bound this particular difference which was first introduced due to the bias introduced due to random reshuffling. So it turns out that the distance between iterates, which are generated by 2 permutations of 1 to n, can be bounded by the number of points where these two permutations differ times the step size plus a factor which comes in due to the zeroth order part of this algorithm. So there are three main elements to prove this lemma. The first thing is, what we need to do is, what we do in this proof is basically we just get rid of all the zeroth order stuff by first bounding the difference between the iterates of an OGD update, which is computed using the exact gradient information, versus the zeroth order update, which is computed by the estimator, which I defined. And the blue term, which I refer here, is precisely coming because of the bias introduced due to the zeroth order operator. And this is again like a usual zeroth order analysis, it's nothing new. The main key challenge here is to compute this difference. We next do is once we obtain a first order OGDA update, we exploit some of the recent characterizations of optimistic gradient descent algorithm, which shows that these optimistic gradient descent algorithms can be thought of as an approximation of the proximal point algorithm, which I think one of the speakers talked before me. Simply because the exact proximal point method you cannot use, because proximal point method is computationally expensive. You have to solve an implicit equation in every time step. So it's good to characterize the difference between OGDA and the proximal point method. And then using the fact that the iterates which are generated by the proximal point method, you can show that the proximal point operator will be non-expansive if the two permutations agree. So for example, if I use the same data point to update my algorithm, it turns out that the proximal point algorithm will be non-expansive. So that's why we just obtain this first term, which kind of captures, you will only incur an additional error in the difference of iterates whenever the permutations disagree. Okay. So using this sort of ideology here, like to compute the distance between iterates, now I will use these two specific iterates, which as I said in the random reshuffling, the bias introduced random reshuffling, these two iterates S1I and S2I will only differ in 1 point, and that's why this term will essentially go off or become just 1, not go off. And then you have essentially solved the issue of characterizing the difference between the bias introduced due to random reshuffling. Now next comes, once you have characterized how the gap function will look like with and without reshuffling, we'll then capture what would the gap function look like if we had not used the reshuffled variant, or if we just sample a new iteration at every time step as per the stochastic GDA kind of update. It turns out, again here, to compute the gap without reshuffling, we first do the same step of bounding the difference between the OGDA update with the first order information and the zeroth order information. And then, as I said, if you view again the OGDA as an approximation of the proximal point update, following the kind of analysis we have seen for the OGDA update in a recent paper in 2019, we get a standard telescoping sum. And we get
Chinmay,
this.
I think Kostis has 2 questions.
Yeah.
Not sure if you want to ask online.
Oh yeah, sure. Hi, can you hear me?
Yes.
Sorry, I couldn't make it there today because I was teaching until recently. So I was confused. Could you go back to your slide? I was confused about which distributions are you coupling? So you have n data points. So you're comparing a situation where you take a random permutation of your data points versus a batch that is with replacement sampling. So what exactly, could you explain a little bit what are you coupling here?
Yes, so this gap without reshuffling, this term which is gap without reshuffling, this is the exact gap which we evaluate at every point. Okay, and since our loss function is kind of a finite sum structure, which is 1 over n of sum of LIs, this gap function can be thought of as the loss evaluated at a permutation which is sampled at every time step. So if you sample, you can imagine 1 over n of summation of Li as just expectation of the L evaluated at a particular iterate sigma, which is sampled uniformly randomly from 1 to n. So that's what I mean here by saying gap without reshuffling. And gap with reshuffling is just the difference in the loss function, which we obtain by the actual iterates of the algorithm, which we obtain by the following the random reshuffling process.
So S1, just to be clear, S1I is, in the random shuffle, the ith point. So S1I is in one of the epochs of your algorithm, you do a random reshuffling.
Yeah, okay.
S1I is the ith point that you use in your shuffle. What is S2I? It's just a completely random, like what is S2I? It's like, can I think of it? Mm-hmm.
Right. So I think I may not have emphasized this point a lot here. Thanks for asking. So S1I and S2I are both permutations from 1 to n. Okay. And basically by I here, I just denote, you just compute these n tuples of these permutations, which are S1I and S2I. And S1I is basically a uniformly randomly sampled permutation for 1 to n. And S2I is you fix that at a particular iterate, that permutation has a particular value. So it is a conditional distribution in the sense that S1I is a uniformly random permutation from 1 to n, and S2I is that uniformly random permutation conditioned on the fact that one particular iterate or one particular point in that permutation takes a particular value from 1 to n.
Okay.
Yeah, so I think, yeah, so this is not a very good way to write these things because without any notations, but I think these are kind of analysis which people obtain by computing these two iterates, S1I and S2I, even in the random reshuffling with optimization, and then computing a lemma like this, which bounds the iterate difference between the two iterates. So we are just trying to, reflect that ideology here.
Mm-hmm. Okay, thank you.
Yeah, but I agree that it requires some more notations to actually define this object. Thanks for your question. Okay, so that's where I concluded the proof, in the sense that on a high level, the proof idea looks something like this. We know this results, which one can write down, that if your gap function is calculated without any reshuffling, you can use this lemma to compute the gap function as a telescoping sum plus some quantities. And these two quantities, sorry, I missed one point. So this quantity is in the blue, which is we obtain here, is because of the fact that we are using a zeroth order estimator. And that's where, as I said, these etas and epsilon has to be appropriately chosen, as we did in the theorem statement, in order to get the best possible rate in this setting. Okay, so computing the gap without reshuffling is kind of shown by lemma 3. Going from the gap which we get from the reshuffled variant, we use lemma 1 and 2. And at the final time step, as I said, I'll just tune these parameters to compute the final rate. So that's why we obtain the final gap function, which is with reshuffled iterates. This is a very high level proof sketch, but yeah. Okay, so now we just quickly return back to where we started this whole journey with. We are looking at this problem of robust decision dependent machine learning, which is described on this slide. We have conducted some experiments, some initial preliminary experiment for a setting where the learner, if you assume that it's in a realizable setting where you sample theta star from a Gaussian distribution zero identity, and you sample all the features of the data point from the Gaussian distribution, and the labeling is decided by this function, which just captures on which side of theta star xi lies, and plus some error term. So this is like the data set which we created to analyze this algorithm. And the utility function which we obtain, which we assume on the agent's part, takes the similar form as I showed in the previous part where I described the strategic behavior. And here we use a specific form for the numerical experiments that the cost which agents get on changing their features is a quadratic cost, and which kind of every player has a different cost, which is kind of characterized by this variable zeta I. And as I said, this actual utility function is not available at the algorithm designer's hand while designing the algorithm. So one has to just query and work with it. Okay, and it turns out in this, for the simple utility function, you can write the best response. This is just one observation, although we do not use the exact value of best response. Okay, so this is like one of we evaluated these 4 variants of min-max optimization, zeroth order min-max optimization. So basically, we analyze the stochastic gradient descent ascent and optimistic gradient descent ascent, both with and without reshuffling. And we observed that the with reshuffling variants kind of perform better than without reshuffled variants. But there's also one more interesting observation here, that a naive stochastic gradient descent ascent algorithm kind of performs at par with the optimistic gradient descent ascent algorithm. This is what we leave as a future work right now. We do not have an exact analysis of how the stochastic gradient descent ascent will behave with random reshuffling. But the whole idea to take away from this here is that with random reshuffling also, as people observe in the optimization landscape, the same kind of observation holds true in the min-max land as well. And it turns out that since we designed this specific problem formulation where we are robust to any adversarial perturbations to our data set, which is shown in this slide here, where what we observe that as you vary more and more perturbations in your data set, the performance of a naive just decision dependent machine learning algorithm following the strategic classification literature, we observe that the performance of that classifier decays very quickly as opposed with the perturbations, but the performance of this robust classifier kind of stays, it kind of decays very gradually. So this is one what we would expect if we have designed a robust classifier. Okay, so I'll skip these 2 further experiments in the interest of time. We can discuss this offline. And what I'll want to go over right now is some of the open problems which are there in this domain. So I'll describe the open problems in mainly three categories. One is the algorithmic open problems, other is the modeling open problem. And then I'll go over a more high level picture of how we should be thinking about designing these algorithms, which will be interacting with all of us in a society at large in the coming days, or it has already started. Okay, so in terms of algorithmic convergence, as to the best of my knowledge, the convergence of zeroth order method for min-max optimization for a non-convex, non-concave objective is a largely open problem. People have analyzed variants. For example, in this work, we analyzed convex-concave variant. People have analyzed non-convex concave variant or non-convex strongly concave variant, something like that. So yeah, thinking about this and what should be the measure which we use is kind of an open problem here. The other thing is, as I stated, the stochastic gradient descent ascent, which is like a little bit simpler than an optimistic gradient descent ascent algorithm. With reshuffling is also still an open problem. Furthermore, there is a whole lot of work which one can do to design min-max optimization with random reshuffling and talking about variance reductions on top of that. So this is like we have barely scratched a surface in this direction. In terms of modeling, as I said, the model which I presented in the first part of this talk, the agents were considered a myopic agents, with just what they will respond directly to whatever class machine learning algorithm the learner has provided to them. But it is not the setting in a lot of scenarios. People rethink their choices and they kind of reevaluate their decisions, and maybe they get better and change their features for improvement. So one has to think about the strategic decision making with recourse, where people kind of the base distribution of people also shifts based on how they interacted with the mechanism in the last time step, which is kind of largely missing from the literature. On a more like low-hanging fruit in this direction is, in this work, we kind of assumed a Wasserstein ball as a uncertainty set in defining the robust decision-dependent problem. It is, I think, a broadly open problem in a distributionally robust optimization as well, is to come up with a tractable reformulations with different uncertainty set, which I've shown here. There are some operation research people who are actively working on this, but all of their results have just given us a non-convex reformulation of the problem. And this is one of the settings which I presented here, that with Wasserstein metric, we can come up with a convex-concave reformulation, which is tractable. But yeah, in terms of other uncertainty set, it is kind of a largely open problem. Thinking more abstractly, one can talk about settings where we capture the behavioral models where these algorithms will and are interacting with human beings. How to work around with those are kind of a very open questions. Okay, so this is where I will conclude that at this point in the machine learning landscape, where a lot of machine learning algorithms are prevalent in the modern society, kind of lack a lot of aspects which one has to be actively thinking about, be it fairness, be it robustness, be it capturing the dynamical interactions, be it incentivizing the agents for something, some common good and stuff like that. And I think some of the questions we will be discussing in coming workshop on learning in the presence of strategic behavior. And with this, I'd like to thank everybody for listening, and any questions and comments.
All right. Thanks for the very nice talk. Let's see if there are any questions.
Thank you for the nice talk. I would like to ask about an open question that you asked at the end, and I will try a little bit to connect it about the algorithmic perspective of zero-order min-max optimization. So I am wondering, I will try to connect this presentation with the presentation of Visnoy at the start of this today's session. His notion of equilibrium, actually the only point that you cannot take, for example, an adversarial grid equilibrium, is as far as the max player, he used the Monte Carlo method, that is a zero order for the finite differences of the stochastic gradient. The only question is if we have a zero order method to converge to a local minimum, and I think we have that. So in one sense, I think that we have zero order methods that can converge to min-max solutions. Actually, yeah, my question is, what is the min-max solution that you are seeking?
I didn't get the last part. Just we want to solve the saddle point problem of min-max of L of X of Y. But regarding your comment about the zeroth order algorithm for non-convex, non-concave setting, I think I have not seen any paper which has, like most of the recent paper which I was looking at, where as I said, either is imposing some sort of a curvature requirement on either the minimizing variable or the maximizing variable, be it strong convexity or convexity concavity, something like that.
Let me ask the following: can we have assumptions about the ellipticness of the Hessian of the objective function? Yes or no? If you give me, I think that I can create algorithm that can converge at least to the adversarial equilibrium of Visnoy. Maybe we can discuss it offline. I don't know. We'll discuss it offline.
Yeah, I think we should discuss it offline.
Yeah, that would be good because we're running a bit late. And thanks a lot. Like, let's thank the speaker one more time for the nice talk, and we'll reconvene in the afternoon.
Thanks a lot, everyone, for your